The last component of Unit 8 largely involves the topic of rotational inertia. Rotational inertia refers to a measurement of how much an object resists rotation. We can think of rotational inertia as our rotational analog of mass. Because as mass got bigger, if we applied the same amount of force, we would experience less acceleration. Same goes for rotational inertia. Rotational inertia is given by the symbol capital I, and it is measured in SI units equal to kilograms times meters squared. And there are two ways that you can go about solving for an object's rotational inertia. In order to solve for it the first way, we'll break out a solid disk. Solid disk of radius equal to r, and let's say that we have some string wrapped around its perimeter, just like we did earlier in the torque problem. We'll drop that string over a frictionless pulley system and have a force of gravity exerted on this system. Just as before, your force of gravity brings about a net torque in this problem. That's good because the first equation that we use to solve for rotational inertia is net torque is equal to rotational inertia of an object multiplied by that object's angular acceleration. At this point in the curriculum, a lot of people get a little intimidated by the sheer number of different letters and variables, but it's really not that difficult. This is just a rotational analog of force is equal to mass times acceleration. Our rotational analog of force being torque, rotational analog of mass being rotational inertia, and rotational analog of acceleration being angular acceleration. There's many different variables and ways to approach problems like this, such as torque is equal to rotational inertia times angular acceleration. But basically what they all come down to is you'll figure out two of the letters and you'll solve for the third by just plugging it into the equation. The second predominant way to solve for rotational inertia, to me, I would term the shape convention method. That is to say, we work with a lot of consistent shapes in physics class. Four of the most common ones we're about to list. Those are four of the most common shapes that we'll work with. There's this rumor going around that a hollow disk is also known as a ring. And because of the way that the mass is distributed in these objects, their four shapes tend to have pretty consistent rotational inertia values, such to the point that we can come up with four different formulas that are unique to each object. And there they are, four of the more common formulas that allow us to solve for the rotational inertia of an object, measuring the object's mass and the object's length, or perhaps radius. But objects don't exist and rotate in a vacuum by themselves. Sometimes mass is added to spinning objects. So how do you account for added mass when calculating rotational inertia? Well, let's break back out our spinning disk from earlier. If you wish to calculate the rotational inertia of the spinning disk, you would need to find its mass and radius. And you can easily solve for its rotational inertia. But what if we placed an object on the disk? You can think about it like a merry-go-round with a bunch of children on it. The merry-go-round is much easier to push without the children on it, because without the children, the merry-go-round has smaller rotational inertia. But once we place objects on the spinning disk, we increase the rotational inertia. By what factor? Well, all added mass increases rotational inertia by a factor of mr squared. Now that r there does not mean the radius of the disk in this instance. It means the distance that the object is placed from the center of the spinning system. In this case, let's give it a value of r naught. And let's give this child a mass value of m naught. Therefore, our rotational inertia of our spinning disk is no longer simply 1/2 mr squared, but rather 1/2 mr squared plus mr squared, m naught r naught squared, the distance of the child from the center of the spinning disk, multiplied by the mass of the child. While we're on the topic of rotational inertia, we should probably explore angular momentum. Angular momentum is the rotational analog of linear momentum. It is given by the symbol L. It is given units kilograms times meters per second, or times meters squared per second. And it is equal to rotational inertia times angular velocity. Once again, all these letters might seem a little intimidating, but in truth, remember, just angular momentum is our rotational analog of regular linear momentum. And that wasn't too difficult. Momentum is equal to mass times velocity. Angular momentum is predominantly brought up in physical science coursework so that we can get at the conservation of angular momentum, a much more interesting topic. And in order to teach the conservation of angular momentum, we frequently bring up the example of a figure skater. Let's attempt to draw one. Oh no. Initial angular momentum will be equal to the final angular momentum. That's the unpacked form of that equation, or that's the packed form of that equation. Unpacked, that equation looks like this. Without doing too much in the way of calculation, you've seen figure skaters perform this technique before. When our rotational inertia is small, as it is in this instance, the figure skater's arms and legs are held closely to his or her body. As a result, our angular velocity is high and we spin quickly. Whereas on the other side of things, we distribute our mass more outwardly from the axis of rotation for the system, our rotational inertia greatly increases. As a result, we spin more slowly. To look at conservation of angular momentum in more practical classwork style problems, we'll break out that solid disk again. Let's say you have your solid disk and it's spinning freely with no obstructions and no objects tethered to it. We would say that you would have an initial rotational inertia, which can be broken down in this instance into 1/2 mr squared, because we have a solid rotating disk and we can use the shape convention method. Whereas on the other side of this disk, somebody has dropped, let's say, a mass onto the disk. And we now have an object stuck on the top of the disk. The object increases our rotational inertia by a factor of the mass of the disk multiplied by its distance from the center of the rotating system. Solving that out, we have a new final rotational inertia. Unpacked, the equation would look like this. This is a common problem that shows up in homework, quiz, and test problems. You'd probably be asked to solve for something such as, what's the mass of the object that gets attached to the system? Or perhaps, at what distance, forgot to call that R0, at what distance from the center of the system was the object placed? Or perhaps, once the object is placed in the system, what's your final angular velocity? Either way, once you have it set up appropriately, it really is just a matter of plugging and chugging to find the appropriate number.